Hey everybody, I hope you're doing well. In this video, I want to talk about an application of antiderivatives. We will be talking about linear motion. In other words, a particle moving in a straight line. In previous problems, I gave you the displacement function or the position function of the particle, and you were asked to do certain calculations with this. In this particular problem, I'm going to start off with the acceleration of the problem, give you a few little facts about this particle at certain times, and then we're going to come up with some functions about the velocity, the displacement, and then I want to use those two functions to answer a question about the particle moving forwards or backwards. So here's the question that I want to talk about. Suppose I have a particle that moves in a straight line, and it's given by an acceleration function 12t minus 30. I also know that the initial velocity, in other words, when time equals 0, the velocity is 36 centimeters per second. And the initial displacement, or initial position if you want to call it, is given by s of 0, in other words, time is 0 again, and that's 58 centimeters. Now, with these units that I have in this problem, I know my length unit is centimeters, and my time unit is in seconds. So my acceleration units are in centimeters per second squared. I want to answer two things. I want to determine the velocity and the position, and then determine where the particle or when the particle is moving forwards and backwards. So let's get started with this. I know that the acceleration for any time t is given by 12t minus 30. But I also know that the acceleration is the derivative of velocity. So what I'm looking for is the antiderivative of acceleration to get velocity. The antiderivative of 12t is 12t divided by 2. 12t squared divided by 2 minus 30t to the first divided by 1. In other words, it's 12t squared over 2 minus 30t over 1. I can simplify this a little bit more and write this as 6t squared minus 30t. Now, one of the things that we have to be careful about is never forget the constant of integration. Now, I never really mentioned constant of integration before, except for the first video I said don't forget about that plus c. It's technically called the constant of integration. So all said and done, if I write all this down, v of t is going to be equal to 6t squared minus 30t plus some constant. Now, there was some other information given in this problem, and it's right here. V of 0 is equal to 36. So that says if I plug in 0 in here for t, I should get 36. So 36 is equal to 6 times 0 squared minus 30 times 0 plus c. Well, this tells us c is equal to 36. So my velocity function, wrote that a little close there, is 6t squared minus 30t. And now I do not have a plus c anymore because I've done some calculations. We got c is 36. So there's my velocity function. So that answers this first part right here. Now the position function, remember that the position function, the derivative of the position function is equal to the velocity function. So in other words, if I want to figure out the position function, I need to figure out the antiderivative of the velocity function. So here's the velocity function. The antiderivative of this, 6t squared, is going to be 2t cubed. I'm skipping a little step here. 3 times 2 is my 6 if I took a derivative. Minus 15t squared plus 36t plus, now I'm going to write down c again. This c, different c. Traditionally, I just use the same letter. How do I figure out this unknown? Well, that's where this second condition comes in. This says when I plug in 0 for t, my output should be 58. 58 is equal to 2 times 0 cubed minus 15 times 0 squared plus 36 times 0 plus c. This tells us c is equal to 58. So, s of t, writing all this down, is equal to 2t cubed minus 15t squared plus 36t plus 58. So this is the beginning of a linear motion problem. I have a velocity, and now I have a displacement or a position function. So to answer the next part of the question, when is the particle moving in the positive direction? Well, that means velocity is positive. So when is the velocity positive here? So to answer question number 2, I'll do a question 2 in the remaining white space that I have on this page. Positive velocity. I want to figure out where the velocity function is greater than 0. Well, in order to do this, I need to actually set the velocity equal to 0 and solve what is the number between positive and negative? Well, it's 0. This should remind you of the first derivative line stuff that we've been talking about for quite some time now. So when is this function equal to 0? Well, one thing I can do is I can factor out a 6 out of each one of these terms. And I get 6t squared minus 5t plus 6, and that's equals 0. This gives me two values, t equals 2 and t equals 3. You can check this out by factoring, but if I plug 2 in here, I wind up getting 4 minus 10 plus 6, and well, that is 0. So I wind up getting 2, and if I want to talk about derivatives, these are critical values. So the velocity line, I have a 2 and a 3. I know this particle stops moving at time equals 2 and stops moving at time equals 3. I need to pick test values between, well, less than 2, between 2 and 3, and greater than 3. Let's pick a test value, 1. Let's plug 1 into my velocity function. What do I wind up getting? Plugging in 1, I get 6 minus 30 plus 36. I believe I get a positive answer. Picking a number between 2 and 3. Pick a number between, well, greater than 3. I'm going to leave those calculations up to you. So this is where the particle is moving forwards. In other words, in the positive direction. This is backwards. And this is forwards again. I hope you found this video helpful. And if you have any questions, let me know. Have a great day. Bye.